Can you describe for me the difference between 2 pitchers of Kool-Aid? 1 pitcher of Kool-Aid into which we have added, the Kool-Aid mix. We'll make this some sort, well, here's our water. And we'll make this some sort of like wild, crazy, well, grape's my favorite flavor of Kool-Aid. So we've got our grape Kool-Aid flavor packet, same amount in each one. And then we have our sugar, and we'll illustrate our sugar that way. So into one, we've added that much sugar. Into the other, we have put, I don't know, 4 times as much sugar. So, how would you describe the difference between those 2 pitchers of Kool-Aid? Would you say one is sweeter? One with 4 times as much sugar? I would expect it to be sweeter. Maybe did you guys go to Camp Fitch in middle school or elementary? Do you remember drinking bug juice? What is bug juice? Do you know? It's watered down Kool-Aid. They take the Kool-Aid, they make a pitcher of Kool-Aid, and then they add 3 pitchers of water to it. So it's, cut down so that the kids aren't crazy on sugar, but it's still got some artificial colorings to make them a little bit nutty. How would you describe the difference between bug juice and full-strength Kool-Aid?
It's less saturated.
Okay. Well, certainly the bug juice would be unsaturated if we're looking at it as a sugar-water solution. And we don't know what the actual grams of sugar that this solution can dissolve are. That's good. This one might be saturated. It might not. We don't know. This one, if this one is able to dissolve that sugar, then we know that this one certainly is unsaturated. Has the word concentrated occurred to any of you? Is one of these more concentrated than the other? Which one? The one with more sugar. So what we're really talking about when we talk about how strong a solution is its concentration. Okay, so what we're talking about is the concentration of the solution. And in chemistry, a lot of our chemistry is done through the use of solutions. And to figure out the stoichiometry of like how many moles of a substance are available to react, we have to know how concentrated the solution is. If we're having sugar do the reacting, there is more sugar available to react in this pitcher of Kool-Aid than there is in this pitcher of Kool-Aid. So what we're going to start to talk about is molarity. And molarity is the most common measure of concentration. There is another measure of concentration, but we're not going to address it because we're doing the quick and dirty version of events here. Molarity is just the number of moles of solute in a liter of solution. So a 1 molar solution means that there is 1 mole of your solute and there is 1 liter of total solution. So if you wanted to make a 1 molar solution of sodium hydroxide, you would put the molar mass, 1 molar mass of sodium hydroxide, 40 grams, into a flask, and then you would add distilled water up to the 1 liter mark. You don't add a liter of water because the sodium hydroxide is taking up some volume, and you want the total volume of the solution to be a liter. Okay, if you add a liter of water, then you have a weaker solution than you think. Okay. The simple equation for this is that the molarity is equal to the amount of solute divided by the volume of the solution, and that should be centered, but it's not. Oops. And you can rearrange this to solve for anything you want. You can rearrange it to solve for how many liters of the solution do you need to run a reaction. How much solute do you need to put in? It's really easy to make 1 liter, 1 liter of 1 molar solutions. If you're making 250 milliliters of a 0.2 molar solution, the math is a little bit trickier. But fortunately, you've got a simple 3-part algebra equation that you can use to solve for anything. I'll say this again, I already said it once. This is the most commonly used measurement of concentration of solutions. There is another one, which is molality. We are not going to do molality. You should know that it exists. If you're doing anything like molar heat temperature change of, like freezing point change and boiling point change of solutions, you need to know molality, but we're not doing that because we're going to end up skipping those. Molarity is much more commonly used. And therefore I think much more important. But you are going to know how to do that before we leave. So if you would go to page 414 in your book, I would be delighted. Okay, so we've got our formula. We started to list our variables, but we don't have moles, so we have to do a factor label to figure that out. What is the molar mass of sodium chloride? What's sodium? 22.99? Okay, so we have to set up a factor label to figure out how many moles of sodium chloride we have. Well, we have 90.0 grams, 58.44 grams of sodium chloride is 1 mole of sodium chloride. Oops, so we put our molarity is equal to 1.54, etc., divided by 3.5 liters. What you got? 0.4400, etc. How many sig figs do we have? 3. So the molarity of the solution is 0.440. And that is, the units are shown with a capital M. So we would say it's 0.440 molar solution. Okay, I'm going to cut you loose. Assigned problems in the chapter review on this are numbers 15, 16, and 17.